Danielm Moldovan. I'm from the University of Technology, the Distributed Systems Group. And I will be trying to have at least a mix of a more hands-on approach with some videos and like demo where we showcase a bit more the concepts that we just introduced. Of course, this is not only my work, this is joint work done in the department. And I will try to have it, let's say, example-oriented or pilot application focused, where I will describe a bit on what type of Elastic service we will be designing and controlling and how. And of course, try to dive into each individual feature of, like I presented, of the different tools or concepts that we are trying to enforce and develop. So first, we took a, let's say, simplistic but realistic application where you have some sensors that send data to an event processing service, processes data, stores it in a data. Now, to achieve elasticity, actually, you need to have elasticity in mind from the design time of the application to the design time of the monitoring to runtime control and everything. So we view as being a service-oriented field. Everything is a service. We have units. A service unit is a functional block that we say that does something that we consider important. And those units can be structured in topologies. One topology in this case where we apply to cloud can be a particular cloud, so one piece of a service running in one cloud, one in another, or one topology can be a simple data tier, doesn't matter. So to achieve elasticity, we first, of course, need to distribute the data end if we want to have the data in elastic. And in this prototype, we have an installation where we can add and remove data nodes. Usually depending on the load of the application and whatever, this is an elasticity capability that makes sense in this situation. And as I said, you need to design the application so that it can support some elasticity capabilities. I will showcase in this demo only throwing mathematics, so adding and removing virtual machines that run one instance of a service unit. In conceptual view, as Lynn highlighted, you could have more instances of one service unit running in the same virtual machine or in different virtual machines. Of course, we also want the business and the processing part to be elastic, so of course you introduce a load balancer, and then you can add, remove event processing instances behind the load balancer. And of course, everything needs to be configured, so when you add a new virtual machine, if it's a data node, it needs to communicate to the data controller to notify that, okay, I'm a new one, I can start to handle requests. In terms of technology, if you're interested, it's standard or at least usual setup with an HA proxy load balancer, that's simple HTTP load balancer. We have some services that process data, and then Cassandra is distributed data end. Configured to be, although Cassandra is actually ring, configured to be somehow in a master-slave situation where we add data nodes instead. Why do we want this? We want to be able, at runtime, to start with a light initial configuration, very cheap to run, one instance running from each service unit, and then if it's needed, if we have more clients, add a new event processing node, remove it when it's not needed, and if it's, let's say, a really high load, also scale out horizontal scaling, the data, and also the business. Now to achieve elasticity, actually we are trying to provide a platform that, okay, this is a more detailed overview of how we have deployed this application. We are trying to have a platform where a programmer, because we like programming, and although graphical user interface tools are being developed, as you heard yesterday, but we want to have an API, flow-based API, or an easy API, where you can design or describe your application, what are its elasticity capabilities. Then that application should be deployed to a cloud. In this example, we use our private cloud in our department. Then you need to be able to monitor correctly an elastic service. So an elastic service cannot actually be monitored only as we used to do virtual machine level monitoring, throw down and interact with virtual machines, because you need to be able to reason at a service level. Then, of course, you would need some sort of elasticity control that takes elasticity requirements that you design in your service or application and enforces them through the same cloud orchestrator. In terms of deployment, for cloud orchestrator, we are using Salsa. That is a tool that also we mentioned. We have Mela for structuring monitoring information at a higher level, aggregating data, updating and monitoring data, and also analyzing elasticity. And we have our Signal as a runtime to enforce elasticity constraints. The first part that we all want in elasticity is to specify some constraints. And we are able to support, let's say, this is a more simple strategy where you say, in the case my resource is underused, so I have low response time and low throughput, automatically scaling. We also support some a bit more complicated strategies in terms of just minimize cost or maximize performance. But those depend on how do you describe your application and how do you describe the elasticity capabilities and what effect each capability has when you enforce it on the application to be able to reason in this case. We can also specify a more generic constraint that does not say any action, what should be taken. So we also have a little bit of a smart analysis in the control part that says, okay, if this is what you want, we'll analyze all the capabilities and we'll see this is a sequence of actions that might bring the application back in the state in which you wanted, the elasticity state, where everything is how you design it or think it should work. Going just a bit into the domain-specific language that we are trying to build, this is a Java-based implementation. We're still working on it. It's a prototype. It doesn't have all the functionality that it should. But it allows it to define how we want the service to deploy in terms of software stacks. So we run this software scripts to install something. Then if it has some, what in Tosta is a hosted on or connect to relationship. So how does one service unit communicate with another? And then constraints. Constraints and strategies, you can define them on a particular service unit, on a service topology, or the whole service. Of course, you can also define, because you might want virtual machine specific information, or, as I said, topology information. What we still do not have here is how to define custom metrics that you want to collect, and this is done. All our tools are based on XML, so we use XML configuration files to dig into this monitoring thing, but I will show this at runtime a bit later. I will start the demo with a video. It's a bit easier like this. So what we want to do, we want to be able to start and define, I have one service unit, this is a software type, and I want to deploy it like this. I have some sort of software repository from where I can pull some configuration scripts and it should be deployed. In this case, a data controller and a data node. This is the software repository that is embedded in our cloud orchestrator prototype Salsa. And of course, I want also to be able to say, but the data node to be able to scale horizontally needs to know the IP of the data controller to connect to it. That means the other service unit, in this case the data controller, needs to expose such a capability. And the cloud orchestrator needs to be able to inject some contextualization information or whatever information is needed for you to enforce the elasticity capabilities. You can structure these units in a topology, define a service, say what topologies belong to the service, what relationships are this connect to. It will also be a host on a relationship, because in the current prototype we are having we're using a Tosta backend. So the representation for the deployment is a customized version of Tosta that also has something that we need, but basically it has the same relationships. Going after defining this, let's say, standard way, you also are able to define constraints and strategies. So in this case, a service unit is controlled by particular strategy that says whenever the data node is CPU usage less than 40%, scale it. You can also define, and we define here on a topology, a generic constraint where you say, I want all my service units from this topology to have CPU usage maximum 80%. And this is, I'm going with CPU usage because it's a bit easier to understand, but if you go and define after this virtual machine information, if you define the event processing units and the load balancer, just a minute, we go with the response time in this case. So we will have a constraint and a strategy, one constraint on one topology on the data and CPU usage, one constraint on the event processing topology that has a load balancer and an event processing unit, and those will be on the response time. And yes?
May I ask a question?
Yes.
So if you have this kind of constraint, like CPU usage is less than a constant, so does it mean that it will scale in until there is nothing left? Because it's always once it's less than 40%. It's always how do you resolve this kind of
yes, that's why we do not assume that you will be able to know from start all the requirements or the correct requirements. You might do stupid things. As you say, you put less than 80%, and if the system is never loaded, then of course it will scale it. But using, as you will see after we deploy this, you can actually see what or if this requirement was okay for you, if it does not violate or conflict with any other requirement, and then update this.
Another question. Is it possible to have this kind of speed usage, memory usage? Is the single value, I mean, is it for one period of time, or is it somehow related average or some time? Is it like, what are the available constraints?
Exactly. So under the back language for this constraint specification figure, I think also takes into consideration this thing over time. Now, in the demo, I will show which is the current running prototype that is a reactive controller that is in this moment. So it's one monitoring point, actually. But also the monitoring, so the aggregation system is able to aggregate over time. And ideally, you need to be able to enforce overtime and also overtime periods. So this constraint is valid, but between this time hours, or this constraint is valid between these days. That is also, that should be in the future embedded. But this is something, let's say, fresh out of the press. After defining, let's say, all the relationships, everything, it connects to everything. It's hosted on currently, as I said, we don't actually support in this API custom metric composition rules. Those are written back in XML. And also something very important when you want to have a smart controller. You need to have some additional profiling information that you can obtain from a staging or from some hints or gut feelings that actually indicate what is the effect or the expected effect of executing one action on a particular service unit. Of course, this can also be learned over time, but it's something really important in achieving elasticity, because you need to understand how do you want to scale the system, how do you want to reconfigure the system. And I will just try to deploy this, so it's the same thing. Have it deployed. It will take, I think, around 5 minutes, and I would expect this to be a really good point for questions.
Question. Is it like a fresh deployment, or is it modification?
No, it's a fresh deployment, so in our, if it wasn't too fast, everything's building. And the idea is that we are not having the pre-cooked virtual machines. So snapshotted virtual machines that we just instantiate, but we actually create a virtual machine and then deploy the software stack into it. Of course, now I would say a bit, or not as advanced as it should be, but this is the, let's say, salsa view, where you have a virtual machine and you can deploy a layer of software inside it, and then at runtime, when the controller enforces some elasticity action, will use this tool to enforce an elasticity action on the software level or on the VM level, depending on what you want.
And so what we deploy on each particular virtual machine is also defined in Java code.
In Java code, currently you can specify where are your software artifacts or like scripts that you want to run to deploy your software stack. And yes, this is the current status. The idea was that we provide support for you to define some custom installation scripts that are run when you scale the application and also when you deploy initially each virtual machine. Any question? Other questions in this time? Oh, good. So then, I can also, until this allocates, I will go a bit into a next slide that explains one thing that we consider the challenge when we started. So when we started, it was, okay, you are able to control, to get some data, and you scale horizontally out, you replicate, or you add a new data node. Now you have two. You are not interested, or not only interested in the behavior of each individual virtual machine. So with existing monitoring tools or approaches, you can say, okay, that particular instance of the data node behaves in this way, and that particular instance in this way. But you cannot say, this is the general behavior of the data node service unit, or the event processing service unit. So we built Mela, which uses a set of customizable metric composition rules. You can also have default, and we are using some default ones in this demo, where you save from the virtual machines that belong to some service unit. For example, take this metric. In this case, it is also defined by Mela, the number of virtual machines, and perform a sum or an average or a multiplication, and move it to the to the service unit, event processing service unit, or load balancer, or data node. And now you can reason in terms of, let's say, monitoring information that is associated with the abstract structure of the application, not with individual virtual machines. And then you can enrich monitoring information. One very important thing is cost, being able to monitor at least the cost rate. And for example, you can propagate also, again, to the topology level, perform another sum between the service unit level metrics, and multiply them with the cost per virtual machine. And in a, let's say, simple way, see what is the cost per hour, so the rate at which you are using money, depending on your cloud provider and pricing schemes. And even take another metric, like number of connections or throughput, or depending on the application, what is important for you, and get something a bit more relevant. Get cost per client per hour, or something that at runtime might make more sense for an owner of an Elastic application. Because also, maybe the guy that has the Elastic application, the Elastic service has deployed it, does not know requirements on CPU usage, on response time, doesn't care. Maybe he has a simple requirement. Each client of his service, he exposes this Elastic service to a number of people, and each person pays a certain amount of money per hour, or per number of requests, or per month. And he doesn't want to lose money, so what he knows is a requirement over cost, not over response time. And we are also able to enrich monitoring information to get something on which any user or any user of our tools can define any type of restriction or strategy or constraint. Everything should Yeah, it's deployed and running. There are, of course, communication relationships between these things. So, yeah. Just a second. Just a little bit. Of course. Network. Just bear with me 2 minutes. So, as in any cloud, something unexpectedly happened. I guess our cloud orchestrator prototype has a minor issue. Fortunately, then I will go with demo, not live. The idea is that after everything is deployed, then you have monitoring information that is usually associated with a virtual machine, connected back into each individual service unit, and connected into topologies with, this is a constraint. Generic constraints, you don't see single strategies here. So this is something that we consider an elasticity requirement, something that controls the elasticity behavior of the application or of the service. Of course, we go a little bit. If our requirements are not right, the system scales up. But then, let's say that you go and you look at everything and you figure out that actually this is not what you want to do, it's not okay. Then we are also able to, or we support using this API for someone to modify the rules, the strategies, the requirements, and resubmit them to the running system that will reapply them on the fly. Just so in this case, we had a strategy, it's not visible here, that you would scale in this part when the throughput is under 200 and the response time under 200 milliseconds, throughput operations. And then you figure out that this is something that is not right. Because you have 200 throughput, so the system should scale in, but you are actually interested in the average, not in the sum. And this is something that you can customize using our approach, depending on what you want to monitor, on what you want to control, you can define it. And in this case, it also shows that it's important to aggregate virtual machine level monitoring information and consider it associated to the service structure, because you want to take decisions here at this level, not at the level of individual virtual machines. So in this case, you figure out that you need actually the average throughput here. For this, you would go in something that might seem to be XML chaos currently, so define metric composition roots in XML, but at least XML has some nice auto-completion due to its XML schema. So we go and actually configure the composition rules. Of course, there is on the website of the tool, let's say a bit extensive guide on how to configure composition rules. Here we use another one as a base. We apply a different operation, average, so we use the throughput actually. And these operations are predefined. We support a set of predefined operations that can be cascaded. So you can say this operation in a prefix way applied on a set of other operations. And with this particular simple rule, we create for the service unit, for all the service units that, for all the service units that have this metric, throughput, gathered from their virtual machine level, so you can also aggregate metrics between the same level, so from the same service unit, or from underlying virtual machines. When you are at the topology level, you can aggregate from the topology, from the units, also virtual machines. And then again propagate this metric, average throughput, with the same name to the service topology. Yeah, we can control an existing one instead of just deploying. And now you have something that maybe it was more interesting for you from the start. You have also average throughput on which you can modify the previous restriction or the previous strategy that might have not been correctly defined. You would go back using our API, just change the metric on which you want the strategy to be applied, resubmit to a running controller this whole thing. And then RCD, the controller, will take your new strategies on your new metrics and perform an operation that is one operation from the ones that are defined as elasticity capabilities for the service that you are controlling. So it can also take custom operations, of course, if you implement the correct driver. And this is something related to the concept of actually this is the elasticity space. If you look at all the metrics that we have, of all the metrics that we have at the unit level and the topology level or the cloud service, maybe you do not know what requirements you want of those metrics. So maybe you know that you want a response time of less than 1 second, but you have no idea what should be the data latency that ensures that response time. And we use the concept of elasticity space to try to figure this out. We have an implementation in which in which this was the requirement that was put forward around 600 milliseconds, or actually it was 600, but the system detected only around 500 and then 2 large spikes. And for all the other metrics, in this case for the 1 unit, but also for all the other metrics, for all the other units in the overall service, we detect this high and low boundaries. In this case, for example, on the CPU usage, the MELA analysis tool detected that in order to enforce what requirement we put on response time, this is kind of something that we should enforce on the CPU usage. And this is also detected for the other units. So it gives you a rough idea on what should be the behavior of each unit and each topology of the whole service to achieve even a simple requirement. So if you don't know anything about the system or the service behavior, you can say I want this requirement on cost, and then just look what are the detected boundaries for all the other metrics inside your service and refine the control strategies until you get something that you like. And yeah, I'm sorry, it should have been a live demo. It has been running in the last 2 days, but it's always like this. It's like I'm in a course and I'm presenting my work to the teacher, and I swear it has run before. Something, the dog ate it. So thank you for your patience.
Any question?
Yes, please.
I don't need the mic.
Okay.
You were showing the diagram of monitoring where there were multiple nodes going to one particular service. And my question is whether it's still the performance metrics that you get from each machine and you calculate or put the average, or you can actually dig into non-functional requirements and balance, for instance, if there is a requirement for number of transactions per second and it's generated by multiple instances, do you get to that point that you can get those measures, or it's still about having performance?
Actually, whatever, so I'm not sure if it's visible here. Here should also be number of operations, but the idea was whatever you are able to collect. Then currently the prototype uses the Gangla in terms of monitoring collection mechanism. So if you have a plugin for an instance that collects transactions, then that is currently dropped in each virtual machine, let's say metric collection pool, and then you can aggregate it in a higher level, aggregate it here or whatever, or divide it with another unit. The idea was to allow, as you say, anything, and especially not underlying resource performance, because this is something that, let's say, it's easy to get, but something that is application level metric, as you mentioned. And those are more important from one point of view, but also it's important to aggregate the application level metrics and also resource utilization to be able to understand if my number of transactions is too low. Why is that too low? Is the system underused or overused? So there is a complex dependency when you look at the elasticity between different metrics that you collect, or sometimes it is.
I mean, basically in MELA you have some predefined metrics that's based on certain rules, so you can automatically divide such a metric from low level, CPU and so on, based on the topology. But you as a developer, you also can write the composition, what we call the composition operator. For example, you say your matrix is like transaction per minute. It have nothing to do with CPU or whatever. So who do the mapping? So it can be come from the library as a catalog in the system of MELA, or you actually can define by your own. Then you plug into MELA. So MELA do the calculation based on the topology and the user defined operator. Question? So I get everyone tired with 1 hour and a half. So I think this is time for coffee, right? What's that?